Hello everyone and welcome to today's video on L'Hopitals Rule, which is a way to evaluate indeterminate limits. Okay, so let's remember what indeterminate limits are. Over here, I don't know if it's an A or an I, sue me. Indeterminate limits. Okay, this is limits that result in either 0 over 0 or infinity over infinity. Okay, now I'll be completely real with you. The justification for what we're getting ready to learn to fully understand takes a little bit more mathematics than what we currently know. But we can still kind of talk about why this thing is the way it is. So the idea, let's understand 0 over 0, right? The idea is if the top and bottom of a fraction go to 0, then the question is which one approaches 0 faster? Okay, so if the top reaches the bottom, I'm sorry, if the top reaches 0 faster than the bottom, then we're gonna wind up with 0 over something else, which give us a 0. So the result could be 0. We could have a proportionality thing where maybe the top and bottom are off by a factor of 2 or a factor of 1/3 or a factor of 2 over pi or something like that. So that could be the case. And then of course if the bottom is approaching 0 way faster than the top, then we could get an infinite result anyway. So the way that we deal with this, like I was saying, we're comparing the rate of the top and the rate of the bottom. So if f of x is a quotient, let's say we have t for top and b for bottom. So if f of x is a quotient like this, and the limit as x approaches whatever of f of x equals 0 over 0 or infinity over infinity. Okay, then that limit is also going to be the same. Well, in other words, we figure that limit out this way. We take the derivative of the top, we take the derivative of the bottom. In other words, we compare the rate at which the top and bottom are growing or shrinking. Okay, um, and the idea is this is going to be some value, and whatever this value is, that's going to be this. That's going to be what the original limit was. Okay, so even though it was undefined when we first tried it, um, because of relative rates and whatnot, the limit will be the value of the ratio of the derivatives. Okay, and of course, you may have to do this several times. You may have to do this 3 or 4 times before you get an answer. Okay, so be prepared for that. But that's all this thing says. And so we got 3 examples here that we're going to go through. The first one, of course, is probably going to be the most straightforward. We got x to the 9 minus 1. So limit x approaches 1. We got x to the 9 minus 1 over x to the 5 minus 1. And, the idea, of course, is we always want to see if we can plug in 1 directly and get a result. But, of course, 1 to the 9th is 1. 1 minus 1 is 0. 1 to the 5 is 1. 1 minus 1 is 0. So there we go. 0 over 0. We got our indeterminate form. Therefore, we can evaluate this limit where we take the derivative of the top and the derivative of the bottom. The derivative of x to the 9 minus 1 is just going to be 9x to the 8. The derivative of x to the 5 is just going to be 5x to the 4. And, the derivative of 1, of course, is going to be nothing. And now we can simplify here. We're going to get 9 over 5. And then we're going to get x to the power 4. 8 minus 4 is 4. Now, if we plug in 1, right, we're going to get 9 over 5 and then times 1 to the 4th, which is just 1. And we just get 9 over 5. So there we go. One application of L'Hopital's rule. Problem done. Remember, though, we can only use this on 0 over 0 or infinity over infinity. Next, natural log of the natural log of x over x. X approaches infinity. All right, here we go. Limit x approaches infinity. Natural log of the natural log of x over x. All right. Of course, if we do, natural log of, the natural log of infinity, think about the log function. As x goes to infinity, that thing's growing. So natural log of infinity is going to give us infinity. We get infinity down here. This gives us the infinity over infinity that we were talking about. There's our indeterminate form. We need that before we can use L'Hopital's rule. Now that we have that, let's take the derivative of the top. Okay, now this could be tricky if you're not careful. Okay, this is a chain rule once again. Okay, so outside function, natural log. We're going to do 1 over whatever's inside. 1 over natural log. And then we're going to multiply that by, we're going to move inside. Okay, derivative of natural log of x, 1 over x. And then that's going to be it for that. So that's the derivative of the top. Make sure I didn't mess that up. There we go. Over, and now the derivative of the bottom, the derivative of x is just going to be 1. Okay, so that leaves us with 1 over x natural log x. Okay, and now, good. So there's the expression. Now we need the limit, right? So now we need the limit as x approaches infinity of 1 over x natural log x. And that's just going to give us 1 over infinity times infinity again. So 1 over, it's huge. It's huge. It's going to go to 0. Okay? It's going to go to 0. The way to think about that is this. So we could have arrived at that conclusion without going through this procedure, but that's kind of what we're learning right now. So anyway. But the way to think about this is the natural log of x is a very slowly growing function. Remember, the natural log of x is the x value of the exponential function of the e to the x. So this is a very slowly growing function. And then when we take the natural log of that, then that grows even slower. Okay? So natural log of x is already slower than x as is. And then we're taking the natural log of that and making it even slower. So the bottom is going to grow way faster than the top, which means we're definitely going to have 0 for that limit. Okay? We could have reasoned that out without L'Hopital's rule. All right. Next. Good old inverse trig, inverse sine of x over x. All right, let's come over here. Limit x approaches 0. Inverse sine of x over x. And of course, if we try inverse sine of 0, we're going to get 0 over 0, immediately indeterminate form. So we can immediately use L'Hopital's rule. Take the derivative of the inverse sine. Derivative of inverse sine, of course, is going to be 1 over the square root of 1 minus x squared. Okay, that's the derivative of the top. We're going to divide that by the derivative of the bottom. Derivative of x is going to be 1. All right. So now we need the limit as x approaches 0 of that function of what we have, 1 over the square root of 1 minus x squared. And now if we plug in 0, we're good to go. We get 1 over the square root of 1, which of course is just 1. And so that limit is 1. Okay. And so there we go. We got a nice diverse set of examples here. One as x approaches infinity. We got some polynomials. We got some logarithms. We got some inverse trig. we got the theory of L'Hopitals Rule here. So I think we are good to go. All the other problems should be basically just like this. You may have to, again, you may have to apply this multiple times, but it shouldn't be any different than what we've been doing here. So yeah, I think we're gonna call this video. See you in the next one, everybody.